All right. At this point in the class, having learned as much special relativity as you have, you are probably starting to wonder, how do we know Einstein's equations are validated by experiments? What results are telling us that these equations, which modify Newtonian physics, are really applicable at velocities near the speed of light? One way to validate it is using something called an accelerator, which is a device which can accelerate subatomic particles. And in fact, particle accelerators and colliders test special relativity every day, as I'd like to show you in this lecture. We will take as our example the so-called Large Hadron Collider, which is in Geneva, Switzerland. It's very large, as shown by this photograph here. It's actually an animation showing you particles being injected into a very large ring, red ones in one direction, green ones in the other, which can then be brought into collision at several special locations along the ring where there are experiments located. The ring is very large, as shown here. It's 4.5 kilometers, making this about 27 kilometers in circumference. And it's underground to help shield the radiation from the particles. Before I show you how accelerators can test special relativity, let me just give you a very brief tour of this amazing state-of-the-art accelerator called the LHC. So here's a picture inside the tunnel. As I said, it's about 27 kilometers underground, and that's actually me, a younger me, inside the tunnel next to a magnet and where the beam pipe goes within it. The magnets that are used to bend the charged particles, the protons in this case, around that long ring are very large. So here's an example magnet. It's a dipole bending magnet. It reaches a field of 8.5 Tesla nearly, and it is 15 meters long, or about 50 feet. It also, to operate that strong field, it has to operate at very cold temperatures, just below 2 degrees above absolute zero, and it is a superconducting magnet. But to give you an idea of how large this machine is, we need 1,200 of these magnets lining the machine to bend the charged particles, which is the part of this lecture that we'll show can be used to test special relativity. Now, the LHC made the news some time ago, and one reason it did so was it discovered the so-called Higgs boson in 2012, which confirmed our theoretical understanding and mechanism for mass. We've been using the concept of mass all along in our physics classes, but where does it come from in the theory itself? Well, this Higgs mechanism does provide an explanation, and that was validated in experiments done at the LHC in 2012. All right, enough history there and tour. Let's go talk about accelerators. In particular, an earlier name for such colliders was a cyclotron, and that was because the frequency had to be cycled as particles went around the ring. But let me explain very briefly how such particle accelerators work. There are electric fields used to accelerate the charged particles and give them an increase in their kinetic energy, their momenta. So they'll pass through certain microwave cavities where electromagnetic waves will impart energy to the particles and increase their velocity. But to make them travel in a circular orbit, we need magnetic fields as well to bend them in that circular orbit. So, as an example here, which you might have learned in your introductory physics class, is we have a charged particle coming here with some speed v. If it enters a region of a uniform magnetic field pointing into the screen or out of the screen, it will undergo circular motion within that magnetic field. So imagine this is the ring of the LHC. We need a magnetic field everywhere where that dotted line is, wherever the particle beam is. So the magnetic field is used to bend the particles into a circular orbit. Now we can talk about the orbital frequency. How many times per second do the protons go around the ring? Well, one way to write that down is that frequency is their velocity v over the circumference 2 pi r. Or put another way around, the distance 2 pi r of one orbit times the number of orbits per second is the velocity, meters per second, right? Okay. Now, what have we learned in this course? We've learned about the form for the relativistic momentum p, which is gamma mv, where I'm using v for the velocity of the particle. And gamma is the shorthand 1 over square root 1 over the square root of 1 minus v squared over c squared. It's always a mouthful. Okay, so if I use this definition of relativistic momentum, I can solve for v in my expression for the frequency. V is just going to be p over gamma m, right? So my frequency here can be written as p over gamma m. There's the gamma m, and there's still the 2 pi r. So that's just another way to write the frequency, but now in terms of the momentum of the particles, not explicitly their speed v. All right. Now, another thing you should have learned in your Physics 2 course in Introductory Physics is that when a charged particle enters that magnetic field, it does exhibit circular motion, and this relationship holds here between its momentum p, its charge q, it's the magnetic field b, and the radius of that circular orbit, so this radius r, which for the LHC is actually 4.5 kilometers. It's quite large. So if I take this relationship p equals qbr and plug it over here into f as p over 2 pi gamma mr, I'm going to put basically a qbr in the numerator. And if I do so, I get a qb in the numerator. I had an r, but that canceled the r denominator, so r disappeared. So I have qb over 2 pi m, and then I have a gamma in the denominator, but gamma was 1 over the square root, so 1 over the square root just is the square root of 1 minus v squared over c squared. All right. Now, what's the point of that, right? What is the point? Let's suppose the speed v is much less than the speed of light. If the speed is much less than the speed of light, v squared over c squared is going to be essentially 0. And so I have the square root of 1 minus 0, which is just 1. So when the speed is much less than the speed of light, the frequency of the orbit is just qb over 2 pi m, the charge, the magnetic field, the mass, and 2 pi. It's a constant. In other words, at low speeds compared to the speed of light, the frequency is about constant going around this machine. And so if you had to, for example, to tell when to turn on the electric fields to accelerate the particle at a certain point in the ring, you would do that at a certain fixed frequency. But what happens when v gets close to c? If v gets close to c, v squared over c squared is no longer negligible, and so I'm subtracting from 1, and the square root of something less than 1 becomes smaller and smaller. So now my constant frequency slows down. I have to shift, I have to synchronize the orbital frequency. So in other words, these high energy machines that accelerate particles very close to the speed of light have to synchronize the instrumentation to that orbital frequency that is slowing down because of special relativity. And so such synchronized cyclotrons, the cycling is the cycling of the fields, for example, are known as synchrocyclotrons, or just synchrotrons in short. So basically, the designers of these machines have had to already build in special relativity, because essentially what happens if you inject your particle and it gets near the speed of light, that's a fixed velocity. So it's going to just take a fixed time to go around, okay, around the ring. So that's why the frequency, which might have been a certain value, starts to slow down as the velocity reaches its asymptote. Okay. So that ends this lecture, kind of giving you one application of special relativity that can be tested every day such machines are in operation.